So part two of the presentation deals with the first category of climate engineering technologies, and it involves removing carbon dioxide or possibly not emitting it in the first place. And I'm going to proceed through a number of these technologies, roughly from the more familiar to the less familiar. And the first method is an obvious one, and indeed it's been practiced for centuries, if not millennia, and that's reforestation. So you have a forest that's cut down by a lumber company, and then they plant new trees, and after a certain number of years, 25, 50 or whatever, the trees are in place. And of course, as the trees grow, they absorb carbon dioxide. So they're storing carbon dioxide in solid form, although not forever, because even the oldest trees eventually will die, and then the carbon will be returned to the soil and the atmosphere. Now this technology is quite attractive environmentally, but it's limited in capacity. If we think of the average American who emits 18 metric tons of carbon dioxide per year, you would need 640 trees, roughly, growing at an average rate just to offset the emissions of that one person. Well, if you do the math, you have 330 million Americans. You're going to need an awful lot of trees and area. And then if you extend consideration to the whole world, which now has just over 8 billion people, it's clear that reforestation can only offset a small fraction of the carbon dioxide emissions. So I think it would be categorized as a highly desirable policy, and not just because you're removing carbon dioxide, because the trees provide a natural habitat for species and they're pleasant for recreation, et cetera, et cetera. The second technology is very closely related, and it's called afforestation. Most people probably haven't heard of that. And that also involves planting trees, but in places where there had not recently been a forest, indeed not in human history. Of course, those locations have to be amenable to the forest, but maybe they are with climate change. If it's warmer, maybe the certain types of trees, let's say deciduous trees, can grow now. Right, so that's, if you like, the sister technology to the reforestation. And then you have peatland restoration, and the peatland tends to be marshy places where there's a water base. And if the water drains away, right, because then you lose the water, and then the peat can die, and then the carbon dioxide will be released into the atmosphere. And that is a threat, particularly in northern climates, northern Canada, and in Russia. There was some concern not long ago that with climate change, which is occurring more rapidly at northern latitudes, that a huge volume of carbon in the peat would be released, and that would accelerate climate change in quite a serious way. Another method involves sequestration of carbon in soils, and this mainly entails agricultural methods. So if you low-till or no-till, which means you don't dig the hoe into the ground so much, then there's less exposure of vegetable material which can be emitted into the atmosphere. You can plant perennial crops, right, so that something is being grown all the time, and hence carbon dioxide is being absorbed. And if the land goes fallow, on the other hand, you're going to get releasing carbon. So you want to be absorbing carbon rather than releasing it. And you can also alter planting schedules and rotating crops. So it can be bad to grow the same crop year after year because it drains certain types of nutrients, but you could rotate the crops. Right? So you're getting a steady output from the land, and you're getting carbon dioxide absorption, but the soil is more resilient in the sense that it maintains its ability to feed the crops as the years go by. You can also change the policies for livestock, and they are a major source of emissions of methane, which is a much more potent greenhouse gas than carbon dioxide. I don't have much to say about methane, but it is responsible for something like 15% of greenhouse gas emissions. And there are ways of alleviating it, not only from raising livestock, but also in the oil and gas industry. So not flaring natural gas, for example, which is, of course, wasteful of the resource, and then it releases a lot of the highly potent greenhouse gas methane. Now, the next technology is one which is under rapid development, but so far on a very small scale, and that is carbon capture and storage. All right, so the carbon dioxide in this case is captured not after it's released into the atmosphere, but before. And this is not practical for, say, automobiles, but it is for large stationary users of or emitters of carbon, such as power plants and cement factories. Cement, I think, is responsible for about 9% of greenhouse gas emissions. So when you're building something, you pour a lot of concrete, and then as it sets, a great deal of carbon dioxide is emitted. So if there's some way of trapping the carbon dioxide so it doesn't get emitted, then you're able to reduce the total emissions of carbon. All right, so that's the carbon capture stage of this technology, but then it has to be stored, right? You've got the carbon dioxide temporarily in some kind of a container, but it has to be stored, and preferably forever, or at least over geological time periods. So how can that be done? Well, one way is to store it deep underground, and it could be in natural geological reservoirs where people haven't been before, or it could be in depleted natural gas reservoirs. So there's a lot of space, if you like, underground, and the CO2 can be put into it. So in a sense, natural gas was there, it was extracted, and then you're putting back another gas. And as long as it can be sealed, you don't have water running through it so that there could be leakage, then this is a good way of permanently storing the carbon dioxide. And another possibility is in the ocean, preferably at depth, because if it's done near the surface, it can evaporate out. So that's one means of storage, and the other means is to embody the carbon in products, manufactured goods and so on. Now that may not be permanent, but when the products have reached the end of their useful life, they can be recycled. So the carbon can, in that sense, through the recycling, be kept out of the atmosphere for very, very long periods. Next technology, I'll have little to say about it, and it's called enhanced weathering. And what that involves is taking silicate rock and grinding it into a fine powder. And the silicate rock will absorb the carbon dioxide, and since it's ground fine, it increases the surface to volume ratio, and it's the surface which interacts with the atmosphere. So you're able to increase the absorption rate multifold by grinding it. It's a fairly basic process. And then you just let the silicate rock lie there, and it'll absorb the carbon dioxide, and then it's permanently embodied in the rock. All right, so it's stored for centuries. Next technology is one which has been experimented with, but unsuccessfully, and it involves seeding the oceans with iron. Now, why does that make sense? Well, the iron is a feedstock to a phytoplankton, so the vegetable version of or the plant version of the plankton, and it means that the plankton can absorb the carbon dioxide more rapidly, which of course is a good thing. But there was a test done back in the 1990s where the seeding occurred in a region of the Pacific Ocean, and the trouble was that as the phytoplankton grew, so did the planktonic plants, the planktonic animals, which ate the phytoplankton. So there's only a brief increase in the biomass of the phytoplankton because the predator ate it. So it seems difficult to find a way of avoiding that problem. So seeding the oceans with iron can work. It's been experimented with, but it's not clear that it's a good long-run solution. Next technology is one which is also being actively studied, and it's called direct air capture of carbon dioxide. And that can be done either using solid absorbents or liquid aqueous basic solutions. And this involves chemistry. I don't know about it, but there are these two technologies. And then what's happened when the air is captured, let's say out of a power plant? Well, again, it can be stored underground, or it can be used for products, and in particular for synthetic fuels or in food processing. All right, so if you adopt this technology, it has two benefits. One, it combats climate change, and the other, you get useful products. The big challenge, or if you like, the disadvantage of direct air capture is that it's coming out of the atmosphere, and so far, or as of the last few months, only 424 parts per million of the atmosphere is carbon dioxide. Right, so you have about 1 part in 2,500. So the carbon dioxide is highly diluted in the atmosphere, and hence you have to have a very efficient mechanism of extracting it. It may be possible, but at exorbitant cost. So that's the big challenge. to get the cost down and also the capacity up, so that you can draw out a large volume of carbon dioxide, an appreciable fraction of what's being released. So the current status of the direct air capture is this. You have 18 plants operating around the world. Most of those are in Europe. And in total, they're capturing less than 10,000 metric tons of CO2 per year, whereas the emissions worldwide are over several billion metric tons. So it's a tiny, tiny fraction. However, we have these various technologies, and some are showing promise. And if you scale up the production capacity, you can reduce the average cost. Now, the plan toward meeting net zero emissions by 2015 is to have a lot more plants operating by 2030. That is just from 7 years from now, and reaching a capacity of 60 million metric tons. So that would be a more than 10,000-fold increase in the capacity. Very ambitious, but it may be possible. And it has the advantage that the existing carbon dioxide in the atmosphere can be reduced, and that complements the other policies we've been talking about not emitting it in the first place.